Machine learning-based intrusion detection system for software-defined networks. Abstract. In the last few years, big companies have been depending more and more on software-defined networks SDN to fulfill their needs for programmable networks. But like other networks, SDN has some security problems. Many technologies are used to solve such problems, and machine learning is considered one of the best. Machine learning has proved its ability to find data patterns when other technologies failed. This makes it a perfect choice for anomaly-based detection and intrusion detection system IDS in general. In this research, we propose a new anomaly-based IDS that benefits from the ability of SDN to provide statistical features about every flow that passes through the network, and passes these features to a voting system that consists of several machine learning algorithms, which gives the system the ability to study the user's behavior and predict any possible intrusion. The voting system is trained and tested using NSL-KDD and KDDCup99 datasets, and the results shows increasing in accuracy and decreasing in false positive rate. Keywords: SDN, IDS, machine learning, NSL-KDD. Introduction. The need for programmable networks has drawn the attention of data centers and big data companies to new paradigms like software-defined network SDN, which becomes a trend in the last few years. SDN's main goal is to separate the control and the data planes, with the controller being able to generate and modify the flow tables to suit the network services which are running as applications within the controller. But like every new paradigm, SDN faces many challenges, especially with security. For intrusion detection systems, IDS are considered as one of the best solutions for network security, as it's able to predict and alarm the network administrator about possible intrusions. In the last decade, IDSs are more interested in studying the user's behavior to predict intrusions. Using new technologies like machine learning, which is perfect for such problems as it is able to extract new information with every interaction between the users and the network, and it is able to find patterns in this information which helps studying the user's behavior too. The problem of using machine learning with network security is the need of data extraction from the network, which increases the overhead in it, but after SDN was introduced, it is possible to benefit from its properties, as it provides statistical features about the traffic that passes the network. 1. In addition to the possibility to add the IDS as a program within the SDN controller. 3, which makes it possible to implement an IDS without any additional cost, and without increasing the network latency or decreasing its bandwidth. The rest of the paper is organized as follows. In section 2 we give a brief introduction to SDN, IDS, and machine learning. Related works are introduced in section 3. Our proposed IDS in addition to KDDCup99 and NSL-KDD datasets are introduced in section 4. The performance of our proposed IDS is analyzed in section V. Finally, we draw conclusions in section 6. 2. Background. In this section we briefly present SDN, IDS, and machine learning. Software-defined networks. Software-defined network is a new paradigm in networking that was developed around 2008-5, where SDN controller and SDN switches are the main devices in the network, instead of routers and switches. The key concept of SDN is the separation of the control plane and the data plane, as the controller generates the flow tables and distributes them to the switches, which are only responsible of forwarding the data packets. In addition, the switches calculate statistical information about flows and forward this information to the controller. Table I presents this information. 10. The main benefit of SDN is the ability to add services to the network as applications that run within the controller without adding any devices or modifying the network's topology. 3. This opens a new horizon for improving networks with minimum cost. B. Intrusion detection systems. The intrusion detection is the process of monitoring and analyzing any network event to detect any possible intrusion. It can be classified as host-based when it runs on a network host, or network-based when it monitors network packets. 6. For detection strategy, IDS can be classified as signature-based detection, where it looks for patterns that matches known attacks pattern, and anomaly-based detection, where it looks for patterns that doesn't match normal behavior. 6. Many metrics are used to evaluate the performance of an IDS, but we will focus on accuracy and false positive rate. These two metrics can be calculated from the confusion matrix, which has true positive, TP, the number of attack samples that were classified correctly, true negative, TN, the number of normal samples that were classified correctly, false positive, FP, the number of normal samples that were classified incorrectly, and false negative, FN, the number of attack samples that were classified incorrectly. Accuracy and false positive rate are given in equation 1 and equation 2. Accuracy equals TP plus TN slash TP plus FP plus TN plus FN dot. FPR equals FP slash FP plus TN dot. C. Machine learning. Machine learning is a subfield of computer science that evolved from the study of pattern recognition and computational learning theory in artificial intelligence. It explores the construction and study of algorithms that can learn from and make predictions on data. Machine learning is classified as supervised learning when training data is labeled, unsupervised learning when training data is unlabeled, and semi-supervised when training data is a mixture between labeled and unlabeled data. Many machine learning algorithms have been developed and improved in the last 2 decades. From these algorithms we will use the following. Decision tree, DT. The algorithm chooses the feature with the highest information gain to be the root node, then the Gini index is calculated to find the best partition, then the process is repeated till reaching the specified maximum depth. Random forest, RFA number of decision trees are built depending on a different subset of the dataset for each of them, then the performance of all the trees is averaged to get the final result of the algorithm. XGBoost. A decision tree is built by using a subset of the dataset to get a LEVEL1 decision tree, then other subsets will be used consecutively till reaching a specified level. The algorithm could start with many initial decision trees and choose the best one after a certain level. Support vector machine. SVM depends on finding the best geometric separator between the classes of the dataset by finding the distances between the points of the dataset. The kernel trick could be used by using kernel functions that measures the distances between the dataset points after projecting them to another dimension. Deep neural network. DNN similar to simple neural networks but has multiple hidden layers. 3 previous work. Vineswaran and Purnakandran 7. Introduce an anomaly-based IDS that works in traditional networks and depends on deep neural network model. They use KDDCup99 dataset to train and test the model. The proposed solution gives an accuracy of 93%. They use KDDCup99 dataset, which suffers from imbalance classes and redundant records which affects the reliability of the results. IJERT and Audelian 8. Suggest an anomaly-based IDS that works in SDN and only uses the features provided by it. They compare the results of multiple machine learning algorithms. Random forest algorithm gives the best results, where the true positive rate is 96.3% and the false positive rate is 0.009. The results show the efficiency of depending on the probabilistic distribution using algorithms like random forest. However, in their research, they do not use a standard dataset, which raises some concerns about the validity of their results. Abubakar and Prangono 9. Propose an IDS that works in SDN and consists of a signature-based IDS, and an anomaly-based IDS that depends on deep neural network model and uses NSL-KDD dataset for training and testing. The detection accuracy is 97.4%. However, intrusions detected by the signature-based part are not separated from intrusions detected by the anomaly-based part. So, the accuracy of the anomaly-based part cannot be isolated. Tang and Mamdi 10. Suggest an anomaly-based IDS that works in SDN and only uses the features provided by it. They compare the results of multiple machine learning algorithms. Using a deep neural network with 3 hidden layers gives the best results with an accuracy of 75.75%. However, the parameters of the used algorithms are not provided. So, it is hard to propose a better tuning for the algorithms. 4. Proposed solution. In this section we present the architecture of the proposed IDS, and the datasets used to train and test the machine learning part. A. Architecture. In this section we focus on the design of the IDS. As the input of the IDS is not the whole packets, we need the first part to extract the features. These features can be extracted via the SDN switches. As the extracted features do not need pre-processing, we can directly pass them to the second part, which is a machine learning-based voting system that will produce a prediction on whether the flow is normal or abnormal. This part consists of several machine learning algorithms trained using KDDCup99 and NSL-KDD datasets. Support vector machine algorithm is chosen to cover the possibility of the dataset being geometrically separable. Decision tree, random forest, and XGBoost are chosen in case we can obtain better predictions depending on the probabilistic distribution of the features. Deep neural network is also chosen because it proved its dominance in finding patterns in datasets. The third part is about adding rules that prevents malicious flows from passing the network. Fig 1 shows the architecture of the proposed solution. Fig 1. The architecture of the proposed solution. B. Implementation. As we have seen, the proposed solution consists of 3 parts. Extracting features. In this part we emulate an SDN network using GNS3. The data plane consists of 2 hosts connected to an open switch, an Open Daylight controller that runs on Ubuntu 16.04 Linux distribution, and it is connected to the open switch through OpenFlow 1.3 protocol. Every 2 seconds the controller requests the features collected by the switch using a feature REQ message, OpenFlow message, and the switch replies with a feature reply message containing the features presented in table I. Voting system. This part receives the extracted features and runs them through a set of previously trained machine learning algorithms to calculate the probability of these features being associated to a possible intrusion. The system uses the machine learning algorithms that collaborates to calculate the final decision. Every algorithm predicts new samples individually, and the final prediction is made using the equation 3. Depending on the results of Table 3, and Table 4, and the fact that NSL-KDD is more reliable than KDDCup99, the voting system is implemented using the models resulted from using NSL-KDD dataset. By applying equation 3 to the results shown in Table 4, we get the results represented in Table V. From the results in Table V, we notice that the voting system averages the accuracy of the used algorithms and gives the best FPR compared to the individual results of the used algorithms, as the algorithms with lower accuracy come together to change the vote of the algorithms with the higher accuracy to improve the overall FPR, but this happens at the expense of the overall accuracy. It is always possible to add or remove any algorithm to the voting system in order to trade off between the accuracy and FPR. Conclusions. In this paper we proposed a machine learning-based NIDS for software-defined networks. A voting system is implemented using several machine learning algorithms. This system receives the features provided by SDN, so no more equipment is added to the network, and no overhead packets which increase the network's latency and decrease its bandwidth. Finally, the results show an increasing in the overall accuracy to 79.6% and decreasing in FPR to 0.03, with the ability to trade off one at the expense of the other, by adding or removing algorithms from the voting system.